we have a pendulum. It starts at point A. It's at a certain point. A is obviously not the top. And it has 300 joules. With respect to its lowest point B, it has kinetic energy of 500 joules. Now we know that the kinetic energy at the bottom of the swing is the total mechanical energy because the potential energy of the closed system is equal to 0. And therefore, 500 joules of energy would then be converted into potential, back into kinetic, back into potential. So the mechanical energy of the system is 500 joules. A body slides down a frictionless inclined plane of a constant gradient. For which one of the combinations given below will both physical quantities experience a constant increase in magnitude? They have to keep going up. Acceleration stays constant, so that's definitely out of the equation. And as it goes down, it does increase. It's got to be a constant increase, and kinetic energy is a half mv squared. So if it's mv squared, that's not a constant increase. That's going to be an exponential increase. So kinetic energy definitely has to get out of the system. Acceleration's out of the system. So the only thing left is C. Let's think about it. If I've got a constant acceleration, my velocity will constantly increase, yes, and my momentum, which is equal to mv, there's a direct proportionality between velocity and momentum, and therefore that will also constantly increase. Two objects, R and P, are of equal mass, and they rest on top of a wall that has a vertical height of x. R falls straight down and hits the ground with a certain speed, and P slides down this frictionless incline, which has a length of 2x, as shown in the graph. What is the speed at the bottom of the incline? Now, it doesn't matter what route you take, the mgh at the top is going to be equal to the half mv squared at the bottom. Now, the height is x no matter what. The mass doesn't really matter. G remains unchanged, and therefore, no matter which route you take, your velocity is going to be exactly the same for both by the time they get to the bottom of the slope. This was the absolute mother of a question. It was level 4.17, but let's go through it anyway. Every now and again, we need to be exposed to horrible questions. I'm going to say that, sorry, my pen, EK is equal to a half mv squared. And we know that acceleration is velocity over time, and therefore velocity is equal to acceleration times time. I'm going to therefore put this as a half m at squared. And I'm therefore going to say that that is a half ma squared t squared. Now I'm going to hold this as a constant. And I am going to say that this is y is equal to ax squared. Time is on the x-axis, and kinetic energy is on the y-axis. So those two can be put together, and those two can be put together. Now I'm only considering this a business. A is just is a constant. You know the equation of a parabola looks like that. And a half doesn't change, the mass of the object doesn't change, and they are saying that they want this acceleration to be uniform. In other words, the acceleration needs to stay constant as well. Whether the acceleration is positive or negative, you can quite clearly see it's being squared, which means that it has to become positive. A body's mass has to be positive. A half is positive. So this A has to be positive. Y equals ax squared is a parabola. And in this case, A is positive, and therefore is a smiley face. As a result, that could be half a smiley parabola, that could be half a smiley parabola, that could be half a smiley parabola, that could not be half a smiley parabola. So therefore, C is your correct answer. Yes, I'm aware that that's a horrible question. A railway truck is moving at a constant velocity, and it collides with an identical truck which is stationary. The trucks become coupled and carry on moving in the original direction. Which one of the following combinations would be true of this collision? They become coupled, they stick together, and therefore the kinetic energy is not conserved. But momentum is always conserved in a collision, and therefore D is your correct answer. We've got a projectile. It's fired vertically upwards from the ground. At the highest point of its motion, the projectile separates into two pieces of equal mass. The one piece is projected vertically upwards. After the explosion, the second piece has to go in exactly the opposite direction and with exactly the same momentum. So that is, it has to be projected downwards with the same speed as the first piece. A ball of mass m strikes a wall perpendicularly with a speed of v. It rebounds in the opposite direction with exactly the same speed. So it didn't lose any energy. That was an elastic collision. The magnitude of the change in momentum is equal to final momentum minus initial momentum, which is going to be mv minus m minus v, because this is in the opposite direction, and therefore it becomes 2mv. The operation manual of a car, mass 760 kilograms, claims the car, starting from rest, can reach a certain speed. That's in kilometers per hour. We do not work in kilometers per hour. We need to say 54,000 meters divided by 3,600 seconds, and we get 15 meters per second before we even start. We then say, this is a moving vehicle. The work done is the change in kinetic energy. So it's EK at the end minus the 0 EK at the start, which is going to be a half mv squared. I've got a half, I've got 760, and I've got a final velocity of 15. And I mustn't forget to square it. And I get 85500 joules. We would like to know the power. Power is equal to work done divided by time. Now, lots of you told me that power was equal to force times velocity. You need to get an average velocity. This 15 is a final velocity and therefore cannot be used in there. You would have needed to have said 7,5 if you were going to use that equation. There are quite a lot of ways of doing this question, and I'm showing you one of them. And now I divide that by the 3 seconds, and I land up with 28,500 watts. We've got an experiment to calculate the velocity at which a cricketer can throw a ball. The cricket ball has a mass of 0,4 kilograms. It's thrown horizontally at a ball of clay that is suspended. The clay has a mass of 5 kilograms. When the ball hits the clay, it sticks to the clay. The combination then rises to a certain height. What is the principle of conservation of mechanical energy? There were keywords I needed here. I needed you to be in a closed system. I then needed you to tell me that mechanical energy is kinetic energy plus potential energy, and that it does not get lost in the system. So the sum of the potential energy and kinetic energy remains constant in a closed system would have been a nice definition. Show by calculation that the magnitude of the velocity of the combination at point X is 3 meters per second. So I've got information about this movement here. So I'm just going to use EP at the top is equal to EK at the bottom. I'm going to say a half let's go with MGH, a half MV squared. Nice news, my masses cancel out. 9,8, 0,45 equals a half v squared, and your v turns out to be 2,97. They're asking for the magnitude of the velocity. I could have chopped off a mark if you had given me a direction. Calculate the magnitude of the velocity with which the cricket ball is thrown. Now we are looking at before the collision and during the collision. So now I say that total momentum in a closed system is conserved, and I've got the momentum before is equal to the momentum after, and I then need to say the mass of the ball times the velocity of the ball plus the mass of the clay times the velocity of the clay. Separate objects combine to have a mass ball clay times some or other velocity over there. I know that some or other velocity. I've just worked it out. I have got the fact that this whole system at the beginning is stationary, so I don't even have to consider it, and I simply substitute in 0,4 multiplied by the velocity of the ball before the collision is equal to 2,97 or 3 if you had rounded off. I didn't really mind, although you should keep it in your calculator, multiplied by the combined mass of 5,4, and you land up with that initial velocity being equal to 40,5 meters per second. Again, they ask for a magnitude, and therefore you must not give a direction. We've got a sandbag on a trolley, and it moves down a frictionless inclined plane. When it reaches the bottom of the inclined plane at point B, it continues towards C at a constant speed of 2 meters per second in the direction indicated in the diagram. The sandbag and the trolley have combined mass of 4 kilograms. A bullet then fires into it and gets embedded in the sandbag. Immediately after the collision, the trolley unit travels backwards towards B at 5,3 meters per second. So, I mean, it's all quite convoluted. Calculate the magnitude of the velocity of the bullet just before it hits the sandbag. Well, we know that the momentum before a collision is equal to the momentum after a collision, and therefore we can say that before the collision, we had a 0,15 kilogram bullet traveling at some or other velocity I did not know, plus I had a sandbag trolley combination traveling at -2. It's in the opposite direction, so I'm going to take that way to be negative and this way to be positive, is equal to the two things together, so it's 4,15, and they go towards the right at 5,3. When I rearrange all of that, I find that V comes out to be 200 meters per second, and it's to the right. But they only ask for the magnitude, so once again, I don't put in direction. Show that the kinetic energy of the trolley sandbag combination as it moves backwards along CB towards the slope is 58,3. EK is equal to a half mv squared. This one couldn't have been very much easier. A half the mass combined, 4,15. The velocity that they gave you of 5,3, don't forget to square it, and you get 58,3 joules. And then determine the vertical height of the incline if the trolley now goes exactly to the top up to A. So in other words, this kinetic energy must all become potential energy. So we can say that the potential energy at the top is equal to the kinetic energy at the bottom, and therefore 4,15, 9,8, and we're looking for a height, is equal to, so that was your mgh, is equal to the kinetic energy, 58,3, which I've just calculated, and my height is 1,43 meters. We've got this ball, and it's going to go, it's 80 grams, and it's going to be thrown horizontally. It collides with the wall at 7 meters per second and bounces back. This is an absolutely classic question. You need to get good at it. The change in momentum is equal to the final momentum minus the initial momentum. I'm going to put the mass in there, 0,08. Final momentum is 6 minus 7. I have to change that direction, and then I land up with 1,04 kilograms, 1,04 kilogram meters per second. They want the magnitude and the direction, so I need to consider what happened over here. I got a positive answer. My positive answer was 6 was positive, if you look at it over there. So 6 is away from the wall. And then finally, if during the collision lasts 0,2 seconds, calculate the force, and you know that Ft is equal to change in momentum. I've got that. Change in momentum. I've got a time, and so I can work out the force is equal to 52 newtons, and they only wanted the magnitude of the force, so I can chop off a mark if you put in direction. I only chopped off half, but I can chop off a whole mark.